Right, hello, and welcome back to Real Seekers Beyond. I'm your host, Dale, the Real Seeker, and or really your professor or teacher, teaching my critical thinking and logic course, lecture number 4. And I'll just bring up the slides here, bring that up. So remember last time we learned that there are two different main categories of argument that we're going to be looking at in this course. The first are deductive arguments, which are arguments that are intended to provide logically conclusive support for its conclusion. Whereas inductive arguments are arguments in which the premises are intended to provide probable or likely, but not conclusive support for its conclusion. Now, we learned that deductively strong arguments have to fulfill not one, but two criteria. Number one, they have to be logically valid. Secondly, it has to be rationally justified in terms of one believing that all the premises of the argument are true based on the available relevant evidence. And we started looking at the first criterion for a deductively strong argument, validity. And we learned about the validity test, right? Which is where, look, pretend, if we suppose, pretend, imagine, conceive of, presume, assume, whatever word you want to fill in there, just plug it in. If we just assume that the premises of the argument are true, does that mean that the conclusion is guaranteed to be true as well? It's logically impossible for that conclusion to be false if the premises are true in reality. If you answer yes to that, then the argument is valid. If you answer no, then the argument is invalid. And we started looking at various valid and invalid deductive argument patterns. And we saw last time that there are two main categories of logic that we're looking at least in this course, where by far, the most of the valid deductive arguments that you hear in reality are going to fit into one of these two categories of logic. And we looked last time at about 7 valid deductive argument patterns and a host of invalid ones within sentential or propositional logic, whereby the variables at play, right, represent sentences or propositions or statements, such as, P, and we use the letters P and Q symbolically to represent those propositions or statements, such as, hey, hypothetical syllogism. If Dale jumps in the pool, then he will be wet. If Dale is wet, then he'll need a towel. Therefore, conclusion, if Dale jumps in the pool, then he will need a towel. That's hypothetical syllogism, one of those deductive argument patterns that is valid. And we use, so Dale jumps in the pool. We can represent that by the symbol P. So that's represents a proposition. Then he will be wet. Okay, we can represent that by another letter, Q. If P, then Q. And P and Q stand for propositions or sentences. Whereas predicate logic, which we're going to be looking at in today's class, and certain deductive argument patterns in that branch of logic, the variables, the P's and the Q's are symbolic of not necessarily propositions, but certain characteristics or predicates, quantifiers or attributes and features of certain things. Okay. So that's kind of the difference there. Now, just before we get into predicate logic proper and start looking at some of the valid deductive argument patterns there, just to kind of finish off looking at the sentential or propositional logic, I want to share a concept with you guys about truth tables. That said, before I get into today's lesson, just a bit of review, just kind of a bit of a test for you students. Tyler Fowler, you're my only student at this moment, so this one's for you, and I look forward to hearing your answer. I'm going to play a clip of the dreaded, infamous Orthodox apologist Jay Dyer, and he's debating the atheist T-Jump, and he's providing a transcendental argument. And he makes a claim. He claims that it's a certain type of deductive argument. He even calls T-Jump a dummy for not knowing about this. Let's just say by the end, we'll find out who the real dummy is here. But I don't want to beg the question here. So I'm going to put it to you guys. Here's your first test. I'm going to play this 3 to 4 minute clip. You guys tell me, is Jay Dyer's argument valid or not, or is it invalid? Use your validity test. Secondly, if it is valid, what deductive argument pattern does J claim to use, and is he in fact using that pattern? If he's not using that pattern, what deductive argument pattern from last lecture within propositional logic is J in fact using? So those are your threefold tests, but let's play the clip so you know what we're talking about. All right.
Here's the formal argument. When I say X is Y or all X are Y, that's a distributed property, an attributive property. These are basic logic claims, right? Basic propositional claims.
You've lost me. Is this the first premise?
These are, it's not, I'm giving you a transcendental argument. When I say Z is the necessary condition.
It doesn't have to have an argument. It's just X
Z.
Is what. Yeah, it's an algebraic equation, basically. But yeah, go ahead.
It's not an equation.
Well, I mean, it could be anything, and X could be anything.
I'm illustrating what a transcendental argument is. You want to appeal to Malthus. Even Malthus admit. You want to appeal to authorities. Malthus admits that this is a valid argument.
No, because there's no premise.
Yes, he does. He says transcendental arguments are valid. I'm not talking about the transcendental argument for God. I'm just showing you, because you don't even know what a transcendental argument is.
No, I do know what a transcendental is.
It's a valid form. You don't even know that.
I want to know. You said it's valid form. To have a valid form, what does valid mean? What does valid mean?
Z is the necessary condition.
What does valid mean?
A, therefore Z. It means it's sound. It means it's a sound argument.
What? I'm sorry. What? Go back. What does valid mean?
It means that the conclusion follows from the premise. That's a valid argument.
Yes. That is a valid argument.
Yeah,
so
I'm not putting it in a syllogism right now. I'm putting it in a disjunctive.
Okay,
right? This is a disjunctive, dummy. That's another form of argument. Did you know that?
You said it's valid. So I want to know what the premises are.
It's a disjunctive argument. Do you know what that is? Do you know what that is?
You said it's valid.
It's right here. Z is the necessary condition of A, therefore Z. This is a valid form, dummy. You didn't even know that.
By the way, Chat was laughing at my algebraic equation. I mean, it is an equation. It's a logical equation, but whatever. Go ahead.
This is a disjunctive. It's in logic. It exists. Go look it up.
Mr.
Philosopher. Google real quick. Better Google real quick.
What is premise one?
I'm not putting it in a premise. I'm putting it in a disjunctive.
Jay, what does valid mean? Jay, what does valid mean?
You don't think disjunctive arguments are valid?
Jay, what does valid mean?
Do you think it's a disjunctive argument right here?
Remember, valid means
if you're not, this is a valid argument. You just showed you don't know basic logic because this is valid. This is valid.
All right.
Malthus would say this is valid.
Jay, no, he wouldn't. So
this guy can't argue. He doesn't know basic argumentation. He doesn't know that that's a valid argument.
Can I get my 2 minutes? So
all right. So I'm going to end it there. You have your 3 questions for your little test to see if the lecture from last time is sinking in or not. Go ahead and write down your answers, and then at the end of the video, I will provide you my take on beloved J. Dyer and his transcendental argument here. Sticking within the concept of validity within propositional logic, there is this notion of truth tables. And truth tables are really helpful ways for people to visually see all of the various logically possible options for relationships between the premises and the conclusions and their truth values, to see if an argument, you can check, is it valid or is it invalid? Is it valid or not? And again, recall the various complex statements that we studied in the last lecture, in lecture 3, and their logical operatives. Remember, we looked at about 5 sentential connectives. Negation, not P, represented by the symbol tilde, conjunction, disjunction, conditional, and fifthly, we looked at biconditionals. For simplicity's sake, with respect to truth tables, I'm not going to get into biconditionals. So I'm just going to focus on the first 4 to illustrate a point and keep things simple for you guys at this point. But so we're going to be looking at negation, conjunction, disjunction, and conditional statements. And what can truth tables reveal to us about the truth values for these types of, remember, the textbook calls them compound. I called them, in my lecture, I called them complex statements, right? Complex or compound statements are statements that have 2 or more simple statements that are connected through logical operatives, such as negation or conjunction or disjunction or whatever it is. So here's the table we looked at last time, right? So the ampersand, okay, it represents the conjunction. So it's represented P and Q. Disjunction is the wedge. And remember, we used the inclusive sense there. You have the negation represented by the tilde. You have conditional statements symbolically represented by an arrow symbol, P arrow Q. And there are certain ways that these statements are said to be true. And we're going to take a look at that through truth tables and why this is the case, right? So with a conjunction, conjunctions are false if and only if one or both of the conjuncts are false. Okay? That's the only condition. Disjunctions are the exact mirror image or reverse of a conjunction. Disjunctions are false if and only if both of the disjuncts are false. Okay? So another way of saying this is there's only one way that a conjunction is true. Conjunctions are true if and only if both of the conjuncts are true. Disjunctions are false. There's only one scenario where they're false, if and only if both of the disjuncts are false. And remember, the reason for that is because we use the inclusive, in logic, we use the inclusive sense of or, the inclusive disjunctive, disjunction, which means either P by itself or Q by itself or both, okay? Then you have a negation, which is represented by the symbol, the tilde, not P, right? So it's not the case that John had cake. And these are false if and only if P is true. It's very simple. It's just the opposite and the reverse. And then we have conditional statements, right? If P, then Q. And these are false only under one condition. If and only if the antecedent is true, but the consequent is false. We're going to use truth tables to find out, well, why is this the case? Is this just a rule that logicians like to make up and we just have to memorize it? No, there's a good reason for this, because we can use truth tables to evaluate the logical possibilities. And with negation, just before we get into assessing the truth tables, just be aware that with negation, there are things like double or triple negation or quadruple negation as you get into more, complicated arguments in real life. I'm not going to get into that in this lecture at all. We're keeping things straightforward and simple for the time being. But when you're out there in the wild, so to speak, you're going to get people who are mixed up and well, he's not a good guy. Okay, that's a double negative. So double negatives just translate to meaning the same thing as the original proposition, right? So if it's not A, well, that's the same as saying that it's A. A is true, whatever A is. Okay, or if you have, so anytime if you have an odd number of negatives, so if it's not A, that's the same as saying not A. Or again, if you have 4, any even number, right? If it's 2, 4, 6, 8 number of negations or more, any even number just reduces back down to saying it's true that A, whatever the proposition is. If you have an odd number of negations, then that reduces down to not A. It's false. A is false, whatever that A proposition represents. So that's a simple thing. Again, you're not going to need to worry about that in this lecture, but out in the wild, definitely you'll encounter complex arguments. And maybe we'll see some of that when we get into argument reconstruction and we get beyond just reconstructing these simple, basic deductive and inductive arguments that we're looking at in Unit 2 here. Okay, so let's look at these truth tables. Remember I said conjunctions are true if and only if it's true that both conjuncts are true. Remember, that's the only scenario. Conjunction statements as a whole are false if even one or both of the conjuncts are false. Okay? So you can see, right? My name is Dale, and I was born on April 19th, represented by P and Q. So in the truth table, if you're looking at your slides, you can see, okay, we have proposition P. My name is Dale. Whenever you have two variables, right? Conjunctions present you with two propositions, true statements. There are 4 logical possibilities, right? And you just have to memorize this. So it's either there's 2 logical possibilities where P is true. It's true that my name is Dale. And there are 2 logical possibilities where it's false that my name is Dale. And then with the second thing, Q, representing the proposition I was born on April 19th, there are 4 options there, right? So true, false, right? It can either P is true and Q is true. P is true and Q is false, right? So it's true, my name is Dale, and it's true, I was born on April 19th. Or another logical possibility for a conjunction is it's true, my name is Dale, and it's false, I was born on April 19th. Likewise, it could be false that my name is Dale, but true that I was born on April 19th. And it could be false that my name is Dale and false that I was born on April 19th. So because there are two variables here, there are exactly 4 logical possibilities. And this is going to be the same no matter what type of statement you're looking at. If you're assessing 2 propositions or 2 variables, P and Q, there's always going to be 4 logical possibilities. For simple statements like negations, we'll find out there's only 2 logical possibilities. But let's say we add in, when you're out in the wild, you'll encounter complex arguments with more than just 2 simple statements or simple propositions. Maybe there's 3 or more. So, for example, if you have 3, there would be 8 rows, 8 logical possibilities. And that grows exponentially. If you have 4, then it's up to 16, so on and so forth. Again, just keeping things simple, at the very least for right now. In this lecture, we're just going to stick with 2 variables and 2 proposition statements at the most, okay? So there are 4 logical possibilities at most that we need to consider. So when you have these things separated as simple statements, then you come to assess the truth values of the conjunction as a whole of the statement P and Q, okay? So obviously, as we learned, there's one sense in which a conjunction statement as a whole is true, only if both conjuncts are true. So there we have the top row. P is true, Q is true. It's true, my name is Dale. It's true, I was born on April 19th. Well, therefore, yes, P and Q is true. The conjunction as a whole is true in this case. Every other combination, if it's true, my name is Dale, but false, I was born on April 19th, the conjunction as a whole is false. P and Q is false. And you can see that on your table if you're looking at the slides. Okay, there's another logical possibility. Maybe it's false that my name is Dale, but it's true, I was born on April 19th. Then again, the conjunction P and Q is false as a whole. And if both conjuncts are false, if it's false, my name is Dale, and it's false, I was born on April 19th, once again, the conjunction as a whole is false. P and Q is false as a whole. So hopefully you can see that, especially with the helpful visual table. And this is making sense to you. What about a disjunction? This is the mirror image of a conjunction. Remember, there's only one set of circumstances where a disjunction is false. Statement is false as a whole. If and only if both disjuncts are false. If one or both disjuncts are true, then the disjunction as a whole is true. And that again, remember, that's because in logic, we assume the inclusive, not the exclusive disjunction or disjunctive, right? So it's either P or Q or both means the disjunctive statement is true. The disjunction is true in itself, okay? So here's an example. You can either have a car represented by P, proposition P, or you can have a motorcycle represented by proposition Q. So either P or Q. Okay, we have the same 4 possibilities, right? So P, it could be true that I have a car and true that I have a motorcycle. In this case, P, the statement P or Q or both is true. P or Q is true as a whole here. Or it could be true that I have a car, but false that I have a motorcycle. In this case, the disjunction is true because as long as it's not both, but one of the disjuncts is true here. So that means the disjunction as a whole is a true statement. Or it could be false that I have a car, but true that I have a motorcycle. Once again, the disjunction as a whole would be true because one of the disjuncts is true. There's only one falsification test for the disjunctive statement, and that's where P is false. It's false that I have a car. Q is false. It's false that I have a motorcycle. Both disjuncts are false. Only in that case is the disjunction as a whole false. It's not true that I either have a car or a motorcycle or both. I have none. I have neither of those. So therefore, the disjunction is false. And it's the mirror image. It's the exact opposite of the conjunction, okay? The conjunction, there are three possibilities where a disjunction statement is true and only one where it's false. The conjunction, there are three logical possibilities where the conjunction is false and only one logical possibility where the conjunction as a whole is true. Okay, so they're mirror images. Negations. Okay, so these are simple statements that are denials of a proposition, right? Not P. So it's not true that I am 40 years old. Because of this, because it's a simple statement, there are only two options. P is either true or it's false. It's true that I'm 40 years old, or it's false that I'm 40 years old. And that would mean, translated in terms of not P, the negation statement, it's just the opposite of whatever the truth value is of P. Okay, so if we assume it's logically possible that P is true, if that's the case, then not P must be false. And the other logical possibility, well, if P is false, if it's not true that I'm 40 years old, then that means the negation is true. It is true that I'm not 40 years old. So that's it. That's pretty straightforward in terms of negations, I think. Okay, finally, what about conditionals? Okay, so conditionals, remember, are those if-then statements represented by if P, then Q, which is symbolically the if P, P arrow Q. The arrow represents the if-then logical operator. So we have an example. If Dale jumps in the pool, then he will be wet. This is the same example I used in lecture 3 over and over again. Okay, so we have the same four possibilities. We have two variables. We have P and Q. So two simple propositions or simple statements, right? Simple statement 1 is the antecedent. Dale jumps in the pool. If Dale jumps in the pool, okay, the antecedent, then he will be wet. Second simple statement, he will be wet, represented by Q, and that's the consequent. So there are exactly four options, right? So logical possibility number 1, it's true that I jump in the pool. The antecedent is true. And it's true that I'm wet. Well, in that case, the conditional statement as a whole is true, right? Because remember, the rule is for conditionals, only when because what if-then statements are saying is that the antecedent, Dale jumping in the pool, is sufficient to entail that he will be wet. It's impossible for me not to be wet if I've jumped in the pool. So in this case, the conditional statement's true. But look at the next row. The single condition where a conditional statement is false. If the antecedent is true, if it's true I jump in the pool, but we're saying it's false that I'm wet, well, that's just logically impossible. The conditional statement would have to be false in this case, because it's saying, well, obviously jumping in the pool is not sufficient. It's insufficient because I did jump in the pool and I'm not wet. So in this case, the conditional would be false. And that's the only logical possibility where a conditional statement would be said to be false, as you see in the truth table in row number 2 there. The other logical possibility is, okay, if the antecedent is false, if it's false that I jumped in the pool, but it's true that I'm wet, the conditional still could be true. Right? Because, yes, let's say I'm wet because that heretic David Russell was throwing his immature water balloons at me, and that's why it's true that I'm wet, but it's false that I jumped in the pool. Well, the conditional itself is still true, right? If Mr. Russell tripped on his water balloons and never threw it at me, and because of that I was laughing so hard I jumped in the pool, I decided to jump in the pool, well, then it's still true that if I did that, then I'd be wet. But that's just the counterfactual, right? So in this case, the conditional as a whole is still true. Same deal if the antecedent's false and the consequent is false. If it's false that I jump in the pool and it's false that I'm wet, well, that still means the conditional statement is true. And it could still be true, right? If I jumped in the pool, then that's sufficient to say I'm wet. But as a matter of fact, I didn't jump in the pool, and because of that, I'm not wet. Okay, the conditional statement itself is still true. So it's only when the antecedent is true It's true I jumped in that pool, but the consequent is false. It's false that I'm wet. That the conditional statement as a whole is said to be false, as you can see on row number 2 here. Let's apply these concepts of truth tables to check a deductive argument pattern for validity. Is a deductive argument pattern that we learned last time in sentential or propositional logic, is it valid or not? Well, truth tables can help flesh out or illustrate visually why certain argument patterns are valid versus other arguments are invalid. And to do that, I'm going to just take 2 examples. Let's start with an invalid argument. So premise 1, if the icebergs melt, then the lowlands will flood. Premise 2, the icebergs did not melt. Therefore, the lowlands did not flood. So in symbolic logic, this takes the form if P arrow Q, right? The conditional, if P, then Q. Premise 2, not P, conclusion, therefore not Q. That's what this guy's argument is saying. Now, instantly, if you remember from lecture 3, you'll be going ding, ding, ding. This is denying the antecedent. And denying the antecedent, we learned, is an invalid deductive argument pattern. However, truth tables allow us to visualize why this thing is invalid. Instead of just memorizing that it's invalid, we can visualize. Remember, right? If it's even logically possible for the conclusion to be false, given we assume the premises are true, then an argument is invalid. And truth tables spell out these logical possibilities. So again, we have 2 variables here, right? 2 propositions. Icebergs melting represented by P, lowlands flooding represented by Q. And there are exactly 4 logical possibilities or states of affairs to be the case, given we have 2 variables or given we have 2 propositions at play in this argument. So let's assume the first row, the first logical possibility. Let's say that it's true the icebergs melted, and it's true that the lowlands flooded. Okay, then for the next column, we have premise 1. Now we're assessing the conditional statement, P arrow Q. If P, then Q. If the icebergs melted, then the lowlands will flood. Okay, well, remember what we learned above for conditionals in the truth statements, right? If the antecedent is true and the consequent is true, that means a conditional statement is true. If P, then Q as a whole is true. In this case, the first logical possibility, premise 1, is true. Premise 2 is not P, right? Denying the antecedent. Well, as we can learn in this logical possibility in this row, P is posited to be true here. Therefore, premise 2, not P, is false. Remember, the truth values are literally just flipped when it comes to negations. Okay, the conclusion is not Q. Well, not Q is false in this possibility because this logical possibility entails that Q is true. So therefore, we have premise 1 is true, premise 2 is false, and the conclusion is false. Totally irrelevant for the question of validity or invalidity because we only care about possibilities where both or all of the premises of an argument are true. So this tells us nothing. Let's move on to the second logical possibility. Let's say it's true that the icebergs melted, but it's false that the lowlands flooded. Okay, well, in this case, premise 1, the conditional statement, if the icebergs melted, then the lowlands would flood, is false, right? Remember, there's only one condition where a conditional is false. That's where if the antecedent is true, if those icebergs did melt, that's sufficient to entail that the lowlands will flood. But in this possibility, we're saying it's false that the lowlands flooded. Therefore, the conditional statement as a whole is false in the second row, representing this logical possibility for options or outcomes. What about second premise, not P? Well, once again, that's false because P is posited to be true in this possibility. Therefore, premise 2 is false. Conclusion, not Q. Well, we can see that that's true, right? The conclusion is posited to be true here because we're saying that Q is in fact false in this logical possibility. So we have 2 false premises and yet a true conclusion. Again, is meaningless for the question of checking validity versus invalidity, because we need all true premises and a true conclusion for it to be valid. Okay, what about a third option? Let's say it's false. P is false, right? It's false that the icebergs melted, but it's true that the lowlands flooded. David Russell and his freaking water balloons, I tell you. Okay, so in this case, what about premise one, the conditional statement? Well, that's true, right? Because in this case, we have a false antecedent and a true consequent in this logically possible option, or this logically possibility for outcomes. Okay, so the conditional statement as a whole is still true. Premise one is true. What about premise two? Not P. Well, in this case, yes, we are positing that it's P is false. Therefore, premise two is true. Oh, we've got two premises, and both of these premises are true. Ding, ding, ding. We can check for validity. What do we have about the conclusion, not Q here? Oops, false, right? Because in this logically possible option, Q is true, not Q is therefore false. So we have this row highlighted in red here, where all the premises are true. Both premises are true, but the conclusion is possibly false. Therefore, we know, just getting one row in the red, so to speak, one row where all the premises of an argument are true and the conclusion is false, proves that it's logically possible. Remember, each of these rows represents a logical possibility of outcomes. So therefore, yes, it's a logically possible for both the premises to be true and yet the conclusion to be false. Invalid argument. Bada boom, bada bing, there's the proof in front of your eyeballs. And just to finish this off, okay, well, what if we posit the fourth and last logical possibility, that it's false that the icebergs melted and it's false that the lowlands flooded? Great. So once again, the conditional would be true, right? Because conditional statements are only false as a whole when the antecedent is true and the consequent is false. Well, here both are false, so it's true. The conditional statement itself is true, or it could be true. Not P is true because it's false that P is true. So great, we have two premises. And then not Q is also true because we're positing the possibility that it's false that Q is true. So we have this in the green. But it's important to note we didn't even need to go to this final step, right? If you're doing a shortcut method, which I'll maybe teach you guys about in a future class, so long as there's even one row in red where there's all the premises are true and that conclusion comes out false in a truth table, that's it. It's game over. It is automatically not valid. Okay? You have to have all rows where the premises are both posited to be true, or all the premises of an argument are true, and all of those rows, the conclusion must be true, and only then is it valid. So you must have all rows in green. If you have even one row in red, which I highlight red to show, okay, this is a thing where the premises are true, but the conclusion is false, even one equals it's an invalid argument because there's one logical possibility represented by this row, this red row, whereby the conclusion doesn't inevitably or isn't guaranteed to be true given the truth of the premises. So I hope these truth tables help illustrate and flesh out how we know and why we say certain deductive argument patterns are valid versus invalid. Let's take a look by contrast at a valid example. This will be the last one on truth tables, but premise one, either you will get an A or a C in this logic class. Premise two, you did not get a C. Conclusion, therefore, you got an A. Now, remember, we know from last time in lecture 3, when we studied this is a disjunctive syllogism deductive argument pattern, otherwise known as the argument from elimination. And if you remember, we said, but that's a valid deductive argument pattern. Great. Well, let's take a look at the truth table to figure out why this is a valid option. And let's take a look at all of our logical possibilities. Okay, so we either have option you get an A or the other proposition you got a C. There's two true propositions here. The proposition you got an A, proposition you got a C in this logic class. So there are 4 logical possibilities, right? The first line, okay, maybe it's true that you got an A and it's true that you got a C. Now, again, in English, in the real world, this doesn't make sense because you can't get an A and a C in a logic class. It's an exclusive sense of or. But remember, in logic, unless otherwise stated, and in this class, we're assuming the inclusive sense of or. So that means either you got an A in this class, or you got a C in this class, or you got both. How that makes sense in the real world, no idea. But again, in logic class, just for the sake of argument, we're making the assumption for the inclusive sense of or. That said, if you're out in the real world, I think you would probably apply the exclusive sense to this, just based on the context, because you can only get 1 grade, you can't get 2 grades, so it can't be both. It's either A or C alone. It's not A or C or both. But just for illustration purposes, go with it. Pretend you can get double grades for some reason, okay? Whatever. And this will show how truth tables work to show the validity. Okay, so premise 1, A or C. Did either you get an A or C? Is that true? Yes. Both the disjuncts are true. Therefore, as we learned in disjunction tables, when both the propositions are true, the disjunction itself is true. So great, we plug in a true for that premise 1. Premise 2 is not C. Well, no, that's false, because C is posited to be true in this first logical possibility. And the conclusion, you got an A, that is true in this possibility. So therefore, you have a true premise and a false premise. Okay, who cares about that? That's irrelevant. Next line, maybe it's true that you got an A and it's false that you got a C. So the disjunction itself is true, right? Because one of the disjuncts is true. Disjunctions are only false if both disjuncts are false. Remember, we learned that above in our assessment of the disjunction truth table. Okay, so just to show you guys, yep, so here it is, true, right? When you have a mixture. Okay, the premise not C is true, because in this case, we're saying it's false that you got a C for this logical possibility on this row of the truth table. Great, so we have 2 true premises. And is the conclusion true? Is A true? Yep, A is posited to be true. Boom, it's green. This is a valid thing. Now let's complete the truth table. There are 2 more logical possibilities. Are there any of those possibilities whereby we get 2 true premises? Okay, so let's suppose that it's false that I got an A, but it's true that I got a C. Well, the disjunction is true because one of the disjuncts is true, not both. Both are not false, sorry. And it's false that I did not get a C. Not C is false, premise 2. It's true that I got a C. And the conclusion is false, right? A is said to be false. So this is a mixture. Both premises are not true. It doesn't matter for validity versus invalidity. Final logical possibility in the truth table. It's false that I got an A, and it's false that I got a C. Well, this is the condition where the disjunction is false. With both disjuncts being false, that means either I will get an A or a C in this class is false. Obviously, I must have got a B or a D or an F or whatever. You know, if you're David Russell, you probably got a Z minus or something like that. You know what I mean? But and not C would be true because, yeah, it's false that I got a C. And then A is a false conclusion because A is false. Again, irrelevant. We have a mixture. So there's only one line where one possibility where both premises are true. And that provides us with a true conclusion in this truth table, meaning it's a valid argument. There are no rows of red. There are no rows in this truth table or logical possibilities where both premises are true, but yet we have a false conclusion. And that's how you can use truth tables to help check whether a deductive argument is valid or invalid using certain propositions or sentences in logic. Okay, so that's it for sentential logic. I want to move on to the promised predicate logic category. And we have certain deductive argument patterns that are valid and invalid that we have to learn about from predicate logic. And remember, predicate logic is where the variables don't stand for propositions or statements or sentences. They represent the variables like A or B or P or Q, whatever you put, represent properties, antecedents, attributes, or not antecedents, sorry, properties, attributes, characteristics, things like that. Okay. Okay. So there are only about 4 deductive argument patterns within predicate logic. The first is called a universal modus ponens, kind of similar to modus ponens that we learned about in sentential logic, or affirming the antecedent within sentential or propositional logic. So in predicate logic, universal modus ponens is a universalized version of the modus ponens argument, as it uses a universalized statement, or a universal generalization is the technical term. So where the letters stand for properties or features or characteristics instead of statements or propositions. So here's an example. All A's are B's, X is an A, therefore X is a B. Here's an example. Okay, all students would be represented by the A, are hardworking. Hardworking is represented by the symbol B. John, it represents the symbol X, so John is a student. Therefore, conclusion, John is hardworking. So that's an example of a universal modus ponens. Now, there are similar deductive argument patterns that are invalid on this front, right? So you can have a premise, all A's are B's, X is not an A, therefore X is not a B. And this is invalid. And here's an example. So all students are hardworking, the same as above. Jack is not a student, therefore Jack is not hardworking. Well, it's logically possible for this conclusion to be false, even if we assume both the premises are true. Maybe students aren't the only hard workers in the world. Maybe some lawyers or plumbers are also considered to be hardworking. And let's say Jack's a plumber. He's a hardworking plumber. So that's why it's an invalid pattern there. Another invalid pattern is all A's are B's, right? Premise 2, X is a B, therefore X is an A. So in practical, again, all students are hardworking, premise 1. Tyler Fowler is hardworking. Good on you. Therefore, Tyler is a student. This doesn't follow, right? Both of these premises could be true. But maybe Tyler is one of those hardworking plumbers, or technically speaking, he's a welder. Tyler's not a full-time student. He's a welder, even though he's hardworking. And it's true that all students are hardworking, let's just say for the sake of argument. So that is an invalid deductive argument pattern within predicate logic here, okay? So hopefully you can see that, right? Yes, Tyler's hardworking, but he's a hardworking welder. He's not a student. He doesn't have to be a student. And here's a good way of representing this visually. Look at your slides if you're listening to this, because I have a helpful Venn diagram or circle diagram that'll help you see why this is the case, right? So in this case, B is representing everyone that's hardworking, and A is representing all the students within that, right? So B is larger. B is larger because, yeah, there's a lot of hardworking. There are hardworking plumbers. There are hardworking lawyers, hardworking heretics. You know, David Russell's definitely hardworking in his heresy there. But and students is only a subset of all the hard workers within B. Okay, so the blue circle A represents all students. The red circle B represents all hard workers. And in this case, the star with universal modus ponens. Okay, great. So this is a valid deductive argument pattern, right? X is an A. John is the star, is an A. He is a student. Since we know all students, every single one of those guys in the blue If you're in the blue circle, you're within the red circle fully. You are a hard worker. But what about the invalid patterns? Okay, again, the circles represent the same thing. In this case, saying X is not an A. So here, X is represented by Tyler. Okay, so shoot, did I mess this up? Tyler, he's within B, right? He's a hard worker, but he's not a student. He's a plumber. So he's outside A. It's possible for him to be outside A. And same with Jack. Jack is not a student. Therefore, Jack is not hardworking. Jack represents the plus symbol. So it's possible to be a B, a hard worker, even though you're not a student and that sort of thing. So that's why these ones are outside of the blue circle, right? They're not students, but they're still within the red. There's no reason to say, well, just because Jack, let me see if I'm getting this right. Just because Jack is not a student, he's not within the blue circle, well, that means he's outside the red circle. No, it's logically possible that he is in the red circle, just outside of the blue. And with Tyler, it's the same thing. Okay, so Tyler is hardworking. So the premise tells us that Tyler is, in fact, in the red circle, right? He's represented by this X. And saying, therefore, Tyler is a student. Well, no, just because Tyler is in the red circle, that doesn't entail that he must be inside the blue circle. So that's how to understand this Venn diagram here that I've created. Again, look at your slides because that will really help you in relation to these valid versus two invalid deductive arguments within predicate logic. Let's look at some more valid, 3 more valid deductive argument patterns in predicate logic. So next we have universal modus tollens. Interesting. Premise 1, all A's are B's. X is not a B. Okay, so you're denying, kind of like you're denying the consequent in sentential logic, right? Therefore, X is not an A. This is valid. And here's an example. All professors are lazy. Professor Dale is not lazy. Therefore, Dale is not a prof. And I think I've represented that. So the star, right? So B represents all A's. All A represents all the professors, right? Fully within the red circle. B represents everyone who's lazy. Okay. All professors are lazy, right? So all the A's are within this subgroup, within this Venn diagram of being lazy, of all the lazy people in the world. Professor Dale, as per premise 2, Dale is not lazy. So I'm outside. I'm outside. I'm the star. Dale is outside of the red circle. I'm not lazy. But therefore, I conclude I'm not a prof because, the blue circle is fully engulfed in the red B circle, right? All profs are within the red B or are lazy, the big lazy category. So there may be lawyers or plumbers that are lazy, stuff like that. And maybe I'm a plumber, but I'm outside this red circle. I'm not lazy, and that's asserted by this premise. So this is valid, right? We know for sure that just if I know for sure I'm not lazy, I know for sure I'm not a professor, even if I call myself Prof. Dale. Next up is universal hypothetical syllogism. Okay, so again, we have the same premise. All A's are B's. All B's are C's as the second premise. Therefore, all A's are C's. So example, all whales are mammals. Premise 2, all mammals are animals. Conclusion, therefore, all whales are animals. This is logically valid, and it's represented here in the Venn diagram. So you have the C, the biggest red circle, which represents all the animals. Then you have the B circle fully engulfed in the red circle, right? Because all B represents the mammals. And then you have the green circle within that, A, which represents all whales. So yes, all A's, all whales are fully in the blue circle. They are all mammals. That's true. And all mammals are considered animals in the larger C within the red circle. There's no part of these circles that is outside of the other. They're all fully engulfed within one another. And this is a valid pattern. Yes, it follows, right? If X is a male, if I put an X here, then yeah, I would follow that deductive universal hypothetical syllogism pattern, okay? So this is true, right? In this case, there is no premise. We're not identifying a thing or an individual. It's all hypothetical, right? Like if I'm an A, then I'm a B. Yep, that's true. If I'm a B, then I'm a C. Great. That means if I'm an A, then I'm also a C. The green circle is fully within the red circle, just as the blue circle, because it's fully within the blue circle. And the blue circle is also fully within the red circle. Okay, so that'll next and last, we have what's called the universal ruling out deductive argument pattern. So this says no, it's a universal negation. No A's are B's. X is an A, therefore X is not a B. And here's an example. So premise 1, no heretic is a saved Christian. David Russell, from the host of the Faith Unaltered podcast, is a heretic. Okay, he is an A. Therefore, David Russell is not a saved Christian. And this absolutely follows. It's logically impossible for the two premises to be true, and yet the conclusion false, right? And here's a helpful Venn diagram, right? So David Russell is within the heretics circle, but from premise 1, we know that no saved Christians, represented by the B blue circle of this Venn diagram, there is no overlap. There is no overlap where we have heretics, but some of them are saved Christians. And remember, David Russell, the X, represented by the X here, is said to be within the A category of being a heretic. So therefore, we know for a fact he is not part of the B group. There's no overlap. He is not a part of the saved Christian group. Sorry, David, just keeping it real. Try to lose the heresy on your Faith Unaltered podcast, and maybe then you could bounce from the red group to the blue group, the heretic group to the saved Christian group. And I know Tyler and I would love to have you on board. So, sorry, me and David Russell. For those who don't know, our Christian apologetics ministry, we always joke back and forth, and he's got his kind of, we have this fun rivalry together. So that's why I'm always picking on Mr. Russell there. So, so I hope that helps. That's it in terms of predicate logic. Those are the only 4 valid deductive argument patterns that you need to know. And there are 2 invalid ones that people usually get correct. So a total of 6 deductive argument patterns, both 4 valid and 2 invalid, that you guys need to learn. And again, use the Venn diagrams to help you understand what's being said here. Okay, so let's move on. In terms of deductive arguments, we've covered validity, okay? And that's everything you need to know about how to tell if an argument is valid or not. But remember, a deductively strong argument must be both valid and rationally justified in terms of one believing all the premises are true based on the available evidence, okay? So what this entails is that there are 3 ways for a deductive argument to be bad. In other words, for an argument to be deductively weak. And I should have highlighted that in yellow, right? So number 1 is, okay, if an argument is invalid, great, game over, you have a deductively weak or a bad deductive argument. But what about the second criterion? Maybe it's valid, but it's not rationally justified for one to believe that one or more of the premises are true based on the available relevant evidence. And if you failed criterion 2, if you failed to read this criteria, then your argument is also deductively weak, whether it's valid or not. Okay? And the third way for an argument to be deductively weak is for both. If it's both invalid and it's not rationally justified, well, then it's a deductively weak argument. Okay, so there are those 3 ways, right? If you have an argument that's invalid but rationally justified, it's deductively weak, not a deductively strong argument. If an argument is valid but it's not rationally justified, then it's deductively weak and not a deductively strong argument. Or if you have an invalid argument that is also rationally unjustified or irrational to believe the premises, one or more of the premises, then it's also deductively weak and not deductively strong. Okay, so there are three ways for deductive strength to fail to obtain. Now, one thing to note here, and this is why I chose to go with deductive strength instead of the criterion of logical soundness, and it's because deductive strength, with the second criterion, there are degrees of justification, right, based on how strong the evidence is and that sort of thing, and that one is aware of. And there is an element of relativity, right, based on the available relevant evidence, right? So remember, justification, as we learned in lecture 2, has no factive component. And this is one of the reasons people say justified true belief is not good enough for knowledge, right? Such as Edmund Gettier. We don't care about that. In this course, we're just assuming it is a justified true belief, but justification doesn't entail the truth of the belief as opposed to something like warrant or another epistemic criterion might. So in this case, to be justified, I just have to be aware of the available relevant evidence and base it on that is available to me. And because of that, it's possible for an argument to be deductively strong for one person, but not another person. Maybe someone else isn't aware of all the available relevant evidence that I am, or maybe he knows more relevant evidence than I do. And on that basis, what's deductively strong argument, an argument may be deductively strong for me or rationally justified for me, but not for someone else. Similarly, with the second criterion, this also allows for some relativity in that maybe for me is the same person, but over time. So an argument may be deductively strong and rationally justified, and therefore deductively strong for me at one time, such as believing in Santa Claus because reliable testimony tells me from my parents that he's real and from the news. And at the same time, at time 2, when I'm an adult, it's no longer deductively strong, right? It's no longer rationally justified to believe that Santa's real. So the evidence, the available relevant evidence has changed. And because of that, an argument that was deductively strong for me at time 1 is no longer deductively strong for me at time 2. So just understand, because of that epistemic criteria that we're assuming justification or justified true belief is knowledge in this course, there is an element of relativity. And that's why I think it's best to use deductive strength as the criteria for a good deductive argument versus, and as well, it recognizes degrees of rational justification too. Whereas soundness just says, well, is it objectively true or not in reality? It has no concern about epistemic criteria, like, about your evidence for believing or you having good reasons for believing that the premises are true. It's just asking, well, are they true or not in reality, kind of thing, right? So that's where soundness, I think, is a bit limited in its scope, and it kind of has to assume or have an add-on or something like that, I would say, right? So that's why we're doing what we're doing. So great. So that answers that. And just, in terms of deductive strength and how it relates to knowledge, I've been going on about this. Remember, validity is absolute. An argument is either objectively valid or it is invalid. But rational justification can come in degrees, as I've said, and there is that relativity, right? And okay, so I've already explained that, right? And remember, in terms of having knowledge, a justified true belief, it doesn't violate. It is possible that a deductively strong argument could have a false conclusion because of fallibilism, right? It's possible to be rationally justified in believing premises are true, even though it's possible that they're false, right? We don't have absolute certainty. And that's called fallibilism, right? You know, if you're 51, if the evidence justifies you believing that you're 62% justified in believing the premises are true, great, that's good enough to count as knowledge, as a justified true belief. In terms of rational justification, remember we have the principles of rational and proportional belief that we learned about in lecture 2. So we base the strength of we either believe if the evidence is more probable than not, or we suspend judgment if it's equal on both sides, for and against, or we disbelieve a proposition if the evidence counts against its truth. We proportion that, the degree of our credence, either belief or discredence or disbelief, based on how the strength of the evidence for or against a given proposition. So again, this is all part of rational justification and explains why there is this relativity as well as degrees that are a part of deductive strength, which I don't think logical soundness gets into at all. Furthermore, it is irrational to disbelieve or suspend judgment about the truth of a conclusion of a deductively strong argument, even if it's possible that the conclusion may be false in reality. Again, if on a balance of probabilities, the evidence supports the truth of the premises, and based on all the available evidence, relevant evidence that you are aware of, and yet you just say, well, I have a deductively strong argument, it's valid, and it's rationally justified for me personally, given the evidence that is available to me, that I'm aware of, and that's relevant to the truth or falsity of the premises. And then you say, well, I'm just going to choose to disbelieve, or I'm just not going to believe and suspend judgment. That's irrational. No, the principles of rational and proportional belief dictate that you must believe in the truth of the conclusion on the basis of your believing the premises are probably true based on the evidence, or are true to whatever degree of strength or credence you have based on the strength of the evidence in favor and or against it. All right, great. So here's kind of a helpful visual way of just understanding the two components of a deductively strong argument versus a deductively weak argument, right? So you have a deductive argument. So the first question is the validity test. Is the deductive argument valid or is it invalid? If it's invalid, it's automatically deductively weak. It's garbage and rubbish. Throw it in the trash bin. Now, if it's valid, great, you're halfway there, but that's not good enough. Then you have to ask, but are the premises am I rationally justified in believing the premises on the basis of the available relevant evidence? If yes, it's deductively strong. If no, then it's deductively weak. So great. So yeah, you have that kind of summarizes in helpful visual form for you guys. So that's it. Next time, we are now finished with deductive arguments. And next time, we are going to focus on the second major category of argument, namely inductive arguments, and learn about that. Thanks for paying attention, and I hope that was helpful. Actually, just before I end, I gave you guys a test with Jay Dyer, the Orthodox apologist, apparently, versus the atheist T-Jump, and their debate. And they talked, Jay Dyer supposedly presented a transcendental argument for the existence of God, which he said was a disjunctive, quote unquote disjunctive. And I had those questions for you guys, right? Is it valid or not? Secondly, is Jay's argument a disjunctive syllogism as he claims or not? Thirdly, if not, what deductive argument pattern within sentential logic is he using? Okay, now for the answer, let's go to my 12-minute clip of me reviewing this little clip of the Jay Dyer versus T-Jump debate and Jay Dyer's transcendental argument. Hint, Jay does not perform so well, logically speaking here. All right, hello, and welcome back to Real Seekers. I'm your host, Dale, the Real Seeker. And today I have a nice short little clip for my critical thinking and logic course. And Last time in lecture 3, we looked at certain sentential deductive argument patterns. And I just want to play this little instructive clip of J. Dyer, the Eastern Orthodox apologist, who I had my own little unfortunate meeting with a while back, versus T-Jump, who I've also formally debated and had a much better conversation with T-Jump, although they both are quite good with rhetorical tricks to win debates and stuff like that, and dominating conversations. But there's an interesting point here that's relevant to certain deductive argument patterns that are common and used in sentential logic. So I wanted to give my take on this and give kind of a logic and lesson, because J. Dyer is quite aggressive against T-Jump, and he's asserting that he's using a deductive argument pattern here. So yeah, let's see if J. Dyer needs another lesson in logic here or not. Let's see what he has to say. Let's first play the clip in full, in context. It's a 3 to 4 minute clip.
Contradiction.
What is your formal argument?
That is a contradiction.
Jay,
that's why you want to shift back to the formal argument.
Jay,
here's the formal argument. Now that you've contradicted, here's the formal argument.
Go for it.
Here's the formal argument. When I say X is Y or all X are Y, that's a distributed property, an attributive property. These are basic logic claims, right? Basic propositional claims.
You've lost me. Is this the first premise?
These are. It's not. I'm giving you a transcendental argument. When I say Z is the necessary condition,
it doesn't have to have an argument.
A,
it's just X
Z.
Is what. Yeah, it's an algebraic equation, basically. But yeah, go
So
ahead.
it's not an equation.
Well,
It's
I mean, it can be anything, and X could be anything.
I'm illustrating what
right.
a transcendental argument is. You want to appeal to Malthus. Even Malthus admit. You want to appeal to authorities. Malthus admits that this is
Okay, let's hear the transcendental argument.
a valid argument.
No, because there's no premise.
Yes, he does. He says transcendental arguments are valid. I'm not talking about the transcendental argument for God. I'm just showing you, because you don't even know what a transcendental argument is.
No, I do know what a
form.
transcendental is.
It's a valid form. You don't even know that.
I want to know. You said it's valid form. To have a valid form, what does valid mean? What does valid mean?
Z is the necessary condition.
What does valid mean?
A, therefore Z. It means it's sound. It means it's a sound argument.
Wrong. Valid does not mean that it's sound. Soundness entails that it's valid, right? Because logical soundness is that a deductive argument is valid and the premises are true. Valid, it doesn't matter whether the premises are true. So J. Dyer, wrong. Perhaps he just misspoke in the heat of the moment.
What? I'm sorry. What? Go back. What is valid?
It means that the conclusion follows from the premise.
That's correct. Yes, that's the definition of valid. If the premises are true, remember our validity test. If the premises are true, then the conclusion must or is guaranteed logically to be true as well. It is logically impossible for the conclusion to be false. So J. Dyer got the definition of validity correct on his second attempt.
That's a valid argument.
Yes, that is a valid argument.
Yeah,
so
I'm not putting it in a syllogism right now. I'm putting it in a disjunctive.
Okay,
right? This is a disjunctive, dummy. That's another form of argument. Did you know that?
You said it's valid. So I want to know what the premises are.
It's a disjunctive argument. Do you know what that is? Do you know what that is?
You said it's valid.
It's right here. Z is the necessary condition of A, therefore Z. This is a valid form, dummy. You didn't even know that.
By the way, chat was laughing at my algebraic equation. I mean, it is an equation. It's a logical equation, but whatever. Go ahead.
Just want to point out interesting Christian charity on J. Dyer's part, calling T-Jump a dummy. Interesting.
It's a disjunctive. It's in logic. It exists. Go look it up, Mr. Philosopher. Google real quick. Better Google real quick.
What is premise one?
I'm not putting it in a premise. I'm putting it in a disjunctive.
Okay, what is valid?
What? So he admits this is an argument, but then he says he doesn't have premises? We're going to find out he does. It's written right there. But what is he talking about? It's a disjunctive argument. He means a disjunctive syllogism. Okay, well, disjunctive syllogisms have premises. Anyways, let's finish off the clip.
Jay, what does valid mean?
You don't think disjunctive arguments are valid?
Hey, what does valid mean?
Do you think it's a disjunctive argument right here?
Remember, valid means the.
If you're not, this is a valid argument. You just showed you don't know basic logic because this is valid. This is valid.
All right.
Malthus would say this is valid.
Jay, no, he wouldn't. So.
Okay, so that's it for the clip. And I just want to say here, it's ironic because Jay Dyer is calling T Jump the dummy. But if I were grading Jay Dyer as a first year university student, F minus on what he just said about this being a disjunctive. He doesn't even know the name. It's called a disjunctive syllogism. That's the name of the deductive argument pattern, okay? Otherwise known as argument by elimination that I taught my class in lecture 3. Tyler, you will know about that, right? Now, let's back up here and take a look at this. First of all, he does have premises, right? He has a therefore. That's Z is his conclusion. Z is the necessary condition of A. That sounds like a premise, right? And then we have premise 2, which is he's affirming A is true. A is true. Okay, now is this a disjunctive syllogism? Nope. I'm sorry, Jay Dyer, you need to go back and do a little bit of a Google search here because you're totally out to lunch. Disjunctives or disjunctive syllogisms or arguments by elimination are of the form A or premise 1, A or B. Premise 2, not A. Premise conclusion, therefore B, or the opposite, right? Either premise 1, either A or B. Premise 2, not B, therefore A. That's what a disjunctive or disjunctive syllogism is. Whereas a disjunctive proper is just the statement, either A or B. It's just that statement, right? So that's what a disjunctive is, and or a disjunctive syllogism that is a deductive argument pattern. This little thing you have up on your pad is not a disjunctive, nor is it a disjunctive syllogism as an argument. F minus J Dyer. What you are putting here, it seems to be, is a conditional. Premise 1 is a conditional, right? You even have the word condition in it, right? Z is the necessary condition of A. So what's another way of translating this? Well, he's basically saying, right, because when you have a conditional statement, right, the if-then statement, basically what this premise is saying here is that, well, if Z is a necessary condition for A, that means that A is sufficient to entail that Z is true. So therefore, the premise 1 here would be if A, then Z. That's what Jay Dyer has written here in a confusing way for people. T Jump's a layman. He's not an expert in logic and stuff. He hasn't taught a course like I have or something like that. So I don't know if people would catch on to that. And I'll be in a future lesson, I'll be teaching you guys about how conditionals work, right? So, but basically the antecedent in an if-then statement or conditional or hypothetical statement, the antecedent is said to be sufficient to entail the truth of the consequent. In this case, A is the antecedent, Z is the consequent. And the consequent is a necessary precondition for the truth of the antecedent. In this case, Z is necessary for A to be true, right? So then it just follows, right? So, okay, if A, then Z. And guess what? Jay Dyer is affirming the antecedent. He's saying, yep, premise 2, A is true. In fact, A is true. And then he goes, therefore, Z must be true, because if A, then Z, right? So that's called a modus ponens, or an affirming the antecedent deductive argument pattern. A totally different argument pattern. It is not there is no disjunctive on this board, and there's no disjunctive syllogism on this board. So, Jay Dyer is kind of saying, well, learn what a disjunctive is, dummy. I repeat the same to you, Jay Dyer. Learn what a disjunctive is, dummy. This is not a disjunctive at all. You've given an modus ponens, or an affirming the antecedent argument. This is just basic logic 101.